Hello, everybody. Welcome to the AI Club. I am Shruitika. I have around 13 plus years of experience in various domains and technologies, have worked with companies like Infi, Accenture, Mindtree, and now I am a freelance trainer on data science. So, in this video, we are going to talk about Genie impurity, information gain, and entropy from a mathematical perspective. In our earlier video, we understood what is the physical significance of these terms. So, just to give a recap of all these terms that we understood in our previous video. So, we learned that entropy is a measure of disorder in a data set. Okay, so entropy is high when there is a higher degree of disorder or the higher degree of impurity. So if we take a data set having blue, green and red balls, while another data set having only blue balls, so then the entropy of first data set is going to be higher than the second data set. Fine. So the next term that we came across was information gain, which can be understood as a statistical property that measures how well a given attribute separates the training examples according to their target classification. So we had understood this thing from a physical standpoint, and then we had a peep through Gini index also. So, what exactly Gini index was? Uh, the Gini index, we sometimes even we call it as Gini impurity. And if a pure data set is there, then the Gini index for that pure data set is going to be zero. Okay, so Gini index, also known as Gini impurity, calculates the amount of probability of a specific feature that is classified incorrectly when selected randomly. Okay, so this is the official definition of Gini index, but in this video, we will try to understand all these terms from a mathematical perspective by taking an example. So, at that time, we also saw that if the entropy for a data set is high, the information is going to be low, the information gain will be low, and the Gini index will be high. So these are the different measures of calculating the disorder or the impurity of a data set. So I hope you are able to see the screen that I have shared. So this is a very good explanation of Gini impurity given by uh, a data, this thing, a programmer, Victor Zhou. So we will go through this blog and try to understand all these terms from the mathematical point of view. Okay, so um, this Gini impurity, information gain, entropy, all these terms are going, you are going to come across when you are doing some decision tree classifier or decision tree regressor. Okay, so just example, if you want to code some program in Python using the decision tree classifier, okay, at that time the different libraries and the functions from those libraries, they will give a simple criteria such as default is equal to Genie. This is something that you will come across when you start coding those things. So we will start from this point, that what exactly this Genie that they have written, so what exactly this means. So decision tree we have already discussed in great detail in our previous uh, video. I hope it is getting properly recorded. Okay. So now let us take a data set. As you can see, a scatter plot is shown here. Okay. So the on horizontal, it is the x-axis, vertical, it is the y-axis, having the scale as 1, 2, 3. Okay. And the points you can see as blue points and the green points. So in order to understand what this data set is, you can imagine that there is a data set having two features. One is x and one is y. and there is one target feature or the target variable which is blue or green. Okay, so ideally in this data set there are three columns. In those three columns, one is the target data set, one is a target column which will have the value of blue or green. Okay, and the rest of the two columns are, let us say, x column and y column. These are the names. Okay, and they will be having some numbers like 1 2 3, as you can see. Okay, so in order to give more clarity to what exactly I am saying, see, there can be one row, okay, which has the value of x column as 0.5. You can see this blue ball. Okay, it is somewhere in between 0 and 1, so maybe 0.5, and the value of y column is somewhere 0.25. Okay, so the x column 0.5, y column 0.25, and the target feature, it is blue. Okay, similarly you can say another row is there in that data set. Okay, where the target column is having the value as green. For that row the value of x is somewhere 2.5, and the value of y is 3. So okay, so in this way you can understand this data set. Now you can see that there are exactly 5 blue balls and 5 green balls here in this data set. Now this is the data set. You can just imagine it to be a CSV file. Just 1 minute. So here you can see that there are 5 blue balls and 5 green balls. Now, so you can also imagine it as around 10 rows in a CSV file, having some x value, some y value, and the resultant blue or green value in the target variable. Okay, so anyway you can, the physical significance I have already shown you using the scatter plot. If you want to imagine it from the CSV perspective, the way we work for a program, this file will be fed as a program, and this file will be fed as an input to a program of decision tree. So anyway anyway you can understand it. So now the thing is, our task is to segregate these rows, okay, so that we are able to predict the whether a ball is blue ball or a green ball depending on the x and the y value. So let us say if we try to make some condition as x is equal to 2, we take the first condition as x is equal to 2, and depending on that, if you want to segregate it, you can see the next scatter plot. Okay, so x is equal to 2, you can say this is our model. On the left side all blue balls, on the right side all the green balls. So this is, from this graph you can say that this is a kind of perfect model, a perfect split that we are able to do. So we will be very easily able to predict if the value of x is less than 2, then it is definitely going to be a blue ball, otherwise it is going to be a green ball. Okay, so this is a kind of perfect split. Now what if we make a split at x is equal to 1.5? As you can see here, the model, if we take as x is equal to 1.5, it is not a perfect split because one of the balls is going to the green area. Okay, the balls, the green balls area it is going, so it is not a perfect split. So now we know that definitely the split, the first split that we have made is better than the second split. Okay, but how to quantify it? And this time we had only around 10 rows and only 2 classes. But what if there are more number of rows and more number of classes? What if there are some more red, purple, and orange balls also? Then it will be very difficult to uh, to decide which will be the perfect split, or if at all, if we are not getting a perfect split, then which is the best split. So in order to quantify it, we have these terms at Gini index or Genie impurity. Fine. So Now here, from a mathematical perspective, they have tried to explain this thing. So what they are saying is randomly pick a data point in our data set, then randomly classify it according to the class distribution in the data set. For our data set, we would classify it as blue 5 by 10 of the time and as green 5 by 10 of the time, since we have 5 data points of each color. So what exactly they are saying is, if we randomly pick up, there are total 10 balls, out of that 5 are blue, 5 are green. So if we want to randomly pick up any ball, what is the probability of the ball being blue? That will be 5 by 10. What is the probability of ball being green? That will also be 5 by 10. Okay, so the first of all we found this probability. Now what is the next thing that they are doing is, now what is the probability we classify our data point incorrectly? Okay, so pick the blue ball and classify the ball as blue. This is 25% probability. How? First of all, the probability to pick a blue ball, that is going to be 50%. Okay. And after picking up a blue ball, we have not seen the color of the ball. Okay, so randomly we picked up the ball, and in reality what is the probability of it being blue? That is 50%. Now the ball is in our hand, we don't know what is the color, and now we want to predict whether the ball is green or blue. So again, the probability that the what we say is blue, that is again 50%. So overall, from the laws of probability, the overall probability to pick up a blue ball at the same time classify it as a blue ball, that is going to be 25%. Okay, similarly pick a blue ball and classify it as green, okay, which is a false thing, false prediction we have done. So this probability is also going to be 25%. Pick green, classify blue. This is again false prediction. This is 25%. Pick green and classify green. This is a correct prediction and this is 25%. So these are the probabilities that we have found. So we only classify it incorrectly in two of the events above. Thus, our total probability is 25% plus 25% is equal to 50%. So the Gini impurity is 0.5% for this class. Okay. So from the a physical point of view, we try to understand what is the Gini impurity. Okay, in this case, we found the Gini impurity as 0.5. So that is what we were discussing also from the official definition of what Gini index or Gini impurity is. It calculates the amount of probability of a specific feature that is classified incorrectly when selected randomly. So classified incorrectly. These are the two ways in which the classification can be incorrect, and we found that this probability is 0.5. Now we will see the same thing from the mathematical perspective. Okay, so the formula for Gini impurity, this we had seen in our previous video also. The formula is sigma pi into 1 minus pi. Okay, and this I is equal to 1 to c. These are the number of the classes that a data set can have. In our case, the number of data sets is only two, that is the blue and the green. Fine. So if we try to calculate the Gini impurity from this formula, probability of blue, probability of picking a blue ball into 1 minus probability of picking a blue ball plus probability of picking a green ball into 1 minus probability of picking a green ball. So this is going to, as you can see here, it is quite clear, and finally we came to the same number, that is 0.5, and both of them are matching. Fine. So this was one of the cases. Now So this 0.5 that we have calculated, it is the Gini impurity of the parent data set, a bucket which is having all the 10 balls, or a CSV file having all the 10 rows, fine. Now we will come to the split. The child buckets where some rows will be segregated depending on some condition. Here the condition that we had used was x is equal to 2. So now we want to calculate the Gini impurity of the two child buckets separately. Okay, so here again we are putting the same formula. Okay, now if you just take these 5 balls, fine, in this the class is going to be 1. Okay, now the here the probability of picking a blue ball out of this bucket is going to be 1. That is what we have written, into 1 minus 1, which is becoming 0, plus probability of picking green ball, it is 0 from this a bucket of blue balls. So finally the Gini impurity on the left is going to be 0, which means that it is a pure data set. Fine. Similarly, the Gini impurity for the right is also going to be 0. Fine. How? The same thing we have done here. The probability of blue in the green bucket is going to be 0. That is what we have written. Plus probability of green is going to be 1, and 1 into 1 minus 1, that is 0. So it means that the resultant data sets, child data sets, have 0 impurity, or they are perfectly pure. So a Gini impurity of 0 is the lowest and best possible impurity. It can only be achieved when everything is the same class. Now let us consider an imperfect split. Fine, where x is equal to 1.5. This is the condition we have applied, and now we want to calculate the Gini impurity of both the child data sets, one on the left and one on the right data set. Okay, now if you see here again, we have applied the formula. Consider the right. First of all, consider the right area. The total number of balls here is 1, 2, 3, 4, 5, 6. Total 6 balls. Okay. And the probability of picking a blue ball here will be 1 by 6. That is what G, right? It is equal to 1 by 6 into 1 minus 1 by 6, plus the probability of picking a blue ball is 5 by 6 into 1 minus 5 by 6. If we complete this calculation, we are reaching somewhere to 0.278. Fine. So these are the child, this is the Gini impurity of the right portion. Now we want to just from the understanding, because it is a very simple data set, we know that x is equal to 2 is going to be the perfect split. But as I said, if there are more number of rows and more number of classes, then it is difficult just by looking at the split to decide which split is the best. And that is where we calculate the Gini impurities, and that is what we are doing. Initially, for x is equal to, initially we calculated the Gini impurity of the parent data set. Okay, and we found that it is 0.5. Then we made a split at x is equal to 2, and we found the Gini impurities of both the left and the right child data set, and we found that the Gini impurity is 0 in this case. Fine. Now again, for another split of x is equal to 2, we are trying to find the Gini impurity of both the left and the right data set. For the right data set, we found that the Gini impurity is 0.278. Okay, so now we have to decide out of both the picks x is equal to 2 and x is equal to 0, x is equal to 1.5, which is the best split. So it is finally time to answer the question we posed earlier. How can we quantitatively evaluate the quality of a split? So here is the imperfect split yet again, the same thing that they have shown. Okay. And left branch, as obvious, Genie impurity is going to be 0, and the right branch we have already calculated the Genie impurity as 0.278. Okay, so next what they have done is they have multiplied these Gini impurities with the number of observations or the number of balls in the data set. So in the left branch, the Gini impurity is 0 and the total number of balls is 0. So 0.4 into 0 plus in the right branch, there are total 6 balls. So 0.6 into 0.278. So finally, we got a Gini impurity of 0.167. So what is the Gini gain? Gini gain is equal to Gini impurity of the parent minus Gini impurity of the summation of all children, right? So the Gini impurity of parent was 0.5, Gini impurity of the summation of all the children was 0.167. So the Gini gain is 0.333 in this case, fine. And if we take the first case, the Gini gain was 0.5 minus 0 because for both right and the left child, the Gini impurity was 0. So in the first case, our gain was 0.5, while in the second case, our gain is 0.33. So definitely the first split is going to be better. And we will always be opting for the better split, that is the first split. So, just if we want to recap, okay, the one thing is there are two terms involved here. One is the Gini index or the Gini impurity, which is the measure of the disorder or the impurity in a data set. Fine. And then the next thing, the term that we found is Gini gain. So Genie gain, as you can understand from the term itself, it is a gain. The gain that we have achieved after the split, the gain in the disorder that we have achieved after the split. So these are two different terms. Don't get confused. One is the Gini index or the Gini impurity, which measures the entropy, and the other is the Gini gain, which we use to decide which split is the better split. Okay, and the Gini gain we get by subtracting the Gini index of the parent from the Gini index of the summation of the children. So that is what we have seen in this blog. Now, the next term that we want to see is information gain. So we will move on to the next blog from the same person and try to understand the information gain also from in a similar way, some mathematical standpoint with some example. Okay, so okay, so this is the blog from the same person and on the same mathematical lines to understand the concept of information gain and entropy. Okay, so some of the text I will just read it out as it is sufficiently explained here, and the remaining things wherever I find the gap, I will try to explain it. So information gain, like Gini impurity, is a metric used to train decision trees. So we saw that Gini impurity, Gini index, and Gini gain, how we can use these terms to decide the split, the best split, which we can use for a decision tree. So just like Gini gain, information gain is also a metric which can be used to train decision trees. So specifically, these metrics measure the quality of a split that we saw in our previous blog also. So the same data points we have taken, as you can see, it is the exactly the same diagram that we have used, that the person had used in the previous blog also. And now we are using x is equal to 1.5 to make the split. You can see it is then imperfect split. Okay, in the left branch you can see only 4 blues, while in the right branch 1 blue is there and the remaining 5 greens are there. So it is not a perfect split, but how to quantify the quality of a split. So on the same lines we are going here also. So before information gain, there is something called as information entropy. Okay, so entropy can be roughly thought of as how much variance the data has. That is the same as how much the disorder the data has. Okay, so a data set of only blues would have very low entropy because the variance is zero ideally in this case. Okay, and a data set of mixed blues, greens, and reds would have relatively higher entropy because there is more disorder that you can see here. Now, if we want to calculate the information entropy, this is the formula, which is a little bit different from the formula that we have seen in the case of Genie index or the Genie impurity. Okay, so here you can see minus and summation of pi log to pi from I to C. So in information in Genie index, you saw pi into 1 minus pi. Here you can see pi log of pi. Okay, so now what they are doing is they have just expanded this formula here because you can see I is the number of classes. So if there are red, blue and green balls involved, then the number of classes are 3. Okay, and in the data set, in the right data set where you can see is not exactly this one, but let us take this data set. Okay, where total 6 balls are there, one blue ball, two green balls and three red balls are there. So now what they have done is probability of picking a blue ball, it is going to be 1 by 6. That is what they have replaced PB with. Then the probability of green is going to be 2 by 6. They have replaced the value of PG with 2 by 6. And the probability of red ball is going to be 3 by 6. That is what they have replaced. And they got an entropy, the information entropy of 1.46. Okay. Now, just for another example, if there are, if only three a data set which has only three blue balls, in that case the entropy is going to be zero. If you can see minus, because the probability is going to be 1, the probability of picking a blue ball from a data set of only blue balls, it is going to be 1, and that is why we arrive at an entropy of 0, which suggests us that there is no disorder or no impurity. Fine, so this is the information entropy that we have achieved. Now, on the similar lines of Genie Gain, so the thing is actually we were finding the information entropy, okay, for this kind of data set where one blue ball is there, one two green and three blue, three green, three red balls are there, and in this case the information entropy that we have found is 1.46. So how we found that thing is, the first thing is we have just expanded this formula, the summation of pi log to pi for I equal to 1 to C, where C are the number of classes. So the probability of picking a blue ball, that is PB log to B plus PG log to PG plus PR log to PR. Okay, and probability of one blue ball is 1 by 6. That is what we have replaced PB with. The probability of green ball is 2 by 6. That is PG is 2 by 6, and the probability of red ball is 3 by 6. And hence we have arrived at a number of 1.46. Okay, at the same time we discussed that if there are three blue balls, okay, there is a data set, okay, having only the same color of blue balls, and that case the information entropy is going to be 0, because the probability of picking a blue ball from a data set of only blue balls is going to be 1. Right, so this point we have discussed. Now moving on. Now we want to find the information gain. Till this point we have seen the information entropy. Now we want to find the information gain to quantify that what is the quality of a split. Fine. So what we have done here, we have again made another split for the same data set with x is equal to 1.5. Okay. And here you can see the probability of, now before the split we had 5 blues and 5 greens. Okay, so the just take the parent data set where 5 blues were there and 5 greens were there. So the entropy of the parent data set is 1. As you can see, the probability of blue ball from the data set was 0.5. So we have just replaced the numbers and we got the entropy as 1. And after the split where x is equal to 1.5, okay, just see this left branch. If we see here, the entropy is going to be 0 because from all these blue balls, this we have seen earlier also, the probability of blue ball is going to be 1 and 1 log to 1 is going to be 0. So this probability will be 0. Now moving on to the right branch, here again total there are, as you can see, total of 6 balls are there. Out of that, 1 blue is there, and the remaining 5 green balls are there. Okay. So in this case, the entropy is 0.65. Now again what they have done is in the left data set there were only 4 balls, okay, which means 40% or 0.5. If we just want to reduce it in the range of 0.1, then 0.4 into 0 plus 0.6 into 0.5, and we are getting the resultant entropy of 0.39 or the resultant information entropy of 0.39. So what is the information gain? It is the parent, for the parent we saw the information gain is 1. Okay, and for the child, that overall the summation for the child, the information entropy is 0.39, so the information gain is 0.61. Okay, so from here, it is clear that in the first case, the information gain is higher, so the first split is better. So, from the discussion about both the information gain as well as the Gini gain, you can see that both of them are same concepts. Okay, only the difference is there in the calculation. In one, we are using the log of probability, while in another, we are using 1 minus the probability. Okay, so you can use any of Gini index, any of Gini gain or the information gain to find which split is the better when you are creating a decision tree. So I hope that these terms of information entropy, information gain, Gini index, then Genie impurity, and then Genie gain, they are quite clear to you from all this discussion. So I hope you are able to solve further more problems from the understanding that you received from this discussion. So thank you all for attending this video.